those two, 420.
I'm super happy to have this kind of daylight here.
So you still didn't have enough of PV? That's great. Come with me and let's finish up this project finally.
What inverters should you choose? Let's walk you through some examples of that. We're going to be looking mostly at hybrid inverters because they not only transform to AC, but they also provide the capability of storing the energy into battery storages. And so that's what we're going to be using in either the case of a fully autonomous off-grid solution or even in the case of a grid-connected solution. So let's have a look at that. Now, one thing to note is that in case of a new build, in case of a design, the intention is, of course, to lower all consumption to the lowest amount possible. And therefore, I have actually seen a autonomous house being built where the aim was to design a single-phase system so that it reduces all the unnecessary costs. And yeah, so that's just one thing to keep in mind. We're gonna distinct three scenarios, two of which are gonna be off-grid, fully off-grid, because I'm a huge fan, just to illustrate that. And so that's in a case we had enough electricity production from the PV in all of the months and a big enough energy storage, which I'm gonna talk about later. And the third scenario is gonna be the most common one, which is gonna be a scenario where the house is still going to be grid connected, but the solar system is going to be added as an addition to that. So first, let's have a look at the autonomous example with three individual single-phase inverters. And this is going to be a solution from VICTRON, which actually provides a great documentation on how to wire them up. The question is, how much power do I need the inverters to have? And we're gonna see that just now. So the total load of all of our appliances based on the load profile would be somewhere around 24.9 kilowatt. The funny thing is that the current state of the grid with the 32 amp three-phase breakers we have cannot afford to power this. So 25 amps times 400 volts times the square root of 3 times 1 simplified for resistive load only gives us about 17.32 kilowatt. And it's acceptable because we don't need all appliances to run at the same time. What we need is to be able to pick which appliances need in every case to be able to run simultaneously. So let's have a look at that. So if we were to sum up the heat source, the heat pump, including all control and measure devices, including some kitchen appliances, while simultaneously running a washing machine and a dryer cycle, we would be getting somewhere around 15.5 kilowatt. So what exact model should you pick? Provided that the phases are equally loaded, which God only knows. The only way to really find out is to measure them. But let's assume that they are. We could be fine with 3 of the 5 kilowatt amp models, or maybe to be more safe in a fully off-grid scenario, the 8 kilowatt amp. Okay, second case scenario, a single device, which there are some available. In fact, there are actually inverters available that have built-in MPP trackers. And so this actually saves us the need to have separate devices for them. There are solutions from SOLAX, which offers up to 30 kilowatt of power in a single device, which is really nice. But now let's have a look at our grid-connected example, which might even be the most common one. And there are devices from KOPP which should come into consideration. They make three-phase hybrid inverters up to 12 kilowatt in power. And what's actually great about this one specifically is that it includes 2 MPP trackers, each one allowing for 2 strings. and a total peak power of 15 kilowatt peak, which would be enough for us. So this actually seems like a great solution. Does it fully cover our load? No. However, in case of a grid connected system, it can serve as a very good support. The only downside is that KOPP does not have transparent pricing on their website, therefore I wasn't able to incorporate it in the budget, which I'm going to show you later. However, they're probably wanting you to reach out to them.
Let's talk a bit of energy storage.
Why we need to store energy in the first place? Well, energy storage in a renewable system works kind of like a balancing measure. So it covers the period where the production from the renewable isn't high enough to meet our consumption. And when there's a surplus, that's the time when it actually accumulates, right? And so with big enough storage, we can even run fully autonomously. However, even if we don't intend to run fully autonomously, it still provides us with kind of an accumulation of power. And so what paths are there to take?
We're going to be talking about standard battery storages. As of now, it's common to use LiFePO4 batteries.
Or convert it directly into heat, well, hot water in a hot water tank. And this is really tied to how other systems in the building are designed. However, there are autonomous buildings with this kind of setup with a hot water tank. The bonus is that you can actually feed in multiple heat sources into that water tank, so you can have whatever other sources of heat, plus, let's say, the surplus from the PV, which actually heats up the water with an electric cartridge. The downside is that it's very difficult to transfer it back to electrical energy, so pretty much after converting it into hot water, you have to emit it somehow, either through radiators, underfloor heating or whatever, or use it for hot water. We're not gonna get into transferring heat from water to electricity. Not very applicable to residential.
We're gonna be also covering hydrogen storages and hybrid battery and hydrogen storages.
Hydrogen! Now we're getting to the fun part. So we've got on one side DC power, which applied to water performs electrolysis, producing hydrogen and some other things. And now hydrogen, the molecules of hydrogen can be actually stored in steel tanks. There used to be underground hydrogen storage tanks. However, there actually are nowadays on the market available products for hydrogen production and storage for residential projects. Very interesting. After converting it to hydrogen, we have two options actually. Either to convert it back to electricity using hydrogen fuel cells, or, which has a higher efficiency, however, I don't really see it being applicable to residential projects, is use a hydrogen gas turbine that converts it to electricity and heat, which overall has a higher efficiency. However, that's not really our case. Works kind of like an engine. What this is good for is that the energy density is pretty much around the energy density of LiFePO4 batteries. And based on market research, there are storages available up to 1 megawatt hour, which would be a solution for the fully autonomous system. Now, what are the downsides? Well, of course, costs. However, there is a bonus in using a hybrid hydrogen plus battery system, which kind of works in a way that the batteries are used for short-term storage and hydrogen is then used for longer-term storage. And with a good control and measure system, this can I can imagine this being very efficient.
And maybe some more creative approaches to that.
Of course, there are creative solutions what you can do with energy surplus. It's really great to have some surplus of energy. Well, in the case that you can store it somewhere, you can run crypto mining rigs, although I'm not sure if I can be talking about sustainability there, because the actual energy consumption of in order to produce a single Bitcoin is getting higher and higher, and therefore it's not not as hot as it used to be. You can also feed the heat into your pool or a whirlpool outside, whatever. Creativity is the limit, or sky is the limit. What did they say? Never mind. If you are still in the design process of the building, you might note that there are other solutions than to installing panels on top of the roofing, which I'm gonna go through just now, which might in the end look a little bit better, provided that you pick something that looks good. Tesla still probably makes the best looking integrated tiles. As you can see, here is an alternative to that, which doesn't really look as good. There are also tiles with integrated hooks, and this is a solution which is not mine. However, we're talking about a custom design used for an autonomous building, in this case actually, where they used the panels themselves as the final roofing layer, and the result just looks pretty damn good. So, after going through the design and picking the integral parts of the system, we ended up with a 25-page long document including the cable routing, etc. And that is without the actual panel layout and without the budget, at which we're gonna have a look at just now.
Great, let's talk investors. Now, we can calculate the budget for this kind of system in material. And now I'm gonna show you that in Excel sheet. And to be honest, it's really a very, very project specific. So it's just for illustration. The prices are converted from Czech crowns to euros based on Czech prices. So you're either way gonna have to budget it based on your project. But just to see what this project may cost in Central Europe, note that this is without the installation works. This is just the material. And we're also going to talk about ROI, although it's not really applicable for this system as the energy, the intention is not to sell the energy. We're going to see how profitable PV systems can be if the energy is sold to the grid.
You might be wondering what a PV system costs. So let's finally have a look at the budget. Now, switching attention here. Do note, this is just for the components, no labor included, although you could budget it based on this. I haven't done that. So let's focus on the components. We've got the 26 Swiss solar panels. We've got this is the version with the 3 pieces of the VICTRON Multiplus 5000 volt amp inverters. We've got the VICTRON, nice. VICTRON MPPT smart solars, 3 of them. And what seems to be necessary based on VICTRON's wiring diagrams are the current sensors, so I included them. What I didn't include is further measuring and control devices, although the inverters themselves should have some capability. And in the bottom, I've also added the Serbo GX, which doesn't seem to be necessary. However, it's there just for reference. Now, we've got the aluminum structures, including connectors. We've got connecting elements, screws, such as things like that. Cabling, DC part. We've also included grounding so that it can be connected to the grounding on the roof. We included cable trays based on this specific project, including screws and angle beams, consoles, stuff like that. Concerning the electrical panel, I selected a 144 module one. This might be a little exaggerated. However, I like always the electrical panels to just have a reserve for future projects, and provided that this project might be extended in terms of the electrical systems, measuring systems, and control systems, it does really come handy. There is nothing worse than not having enough space in the panel or in the rack. So let's just include that. For a simpler system, a smaller one might be used. We've got some AC cabling, and now the rest is pretty much project specific. There is some ventilation adjustment that needs to be done, and I selected some fancy copper cable trays because they're going to be run in the interior, and this is just a design thing to say, including the servo. And there's also some gear. Now this is not all electrical gear one would need to finish this project, but this is a selection of basic gear in order to work with PVs, especially with the MC4 connectors. We've got some crimping pliers, etc., and a test set, and some other things that might be extra. So if we look at it now, as I said, this is just converted from Czech prices, so it means the prices are local and they're specific to this project. But if I converted them to euros, we'd be around 11,740 euros for the basics, and for the total, this is 12,634 euros without labor, without additional measurement devices and control devices. So this is just the realm where you will be headed. One other thing to mention is that the batteries used are 15 pieces of 50 amp hours, so 750 amp hours together, 32 kilowatt hours. Now this is not intended for the system to run fully autonomously. This is just something that might be pretty much okay for a grid connected system. So that's what I came up with. So let's use the 12,000 euros for our further calculations. Nice calculator on pvcalc.org that allows you to calculate the ROI for a given power plant. And now the nice thing is that it accounts for running costs, so maintenance, it accounts for inflation, it accounts for the electricity price and inflation of the electricity price, as well as it allows you to input financing options if you're not financing it from your own funds. However, the trick is that this calculator works as if you were selling all the excess energy to the network. So you could actually be profitable after 3 years in this case. However, this is usually not the case. In our case, we're not going to be selling the energy, so we should be mostly focusing at calculating something like the time that it takes for the power plant to produce enough energy that is equivalent to the price, to the buying price of that system. And so the trick is how to estimate the actual savings. In a fully off-grid system, it's really simple. It's 100% of the induced savings. If you're referencing it to the state when the building was fully grid connected. However, if the building still stays grid connected, it's really tricky, and I would be careful about claiming the 85-90% savings, because without further modeling, you don't really know. And the only precise way is to build a system and measure it. You can model it with some kind of software, but we don't have that available. So I'm just gonna say this. If the savings induced by the systems were 75% of the yearly energy consumption, 11.6 years. If it were 85%, we'd be getting closer to 10 years. Now, what about the lifespan of the components? Now, as we've seen, the panels have a 20-year warranty and a 30-year power warranty, which is pretty nice. And one thing to note is that the panels are probably gonna live for much longer. It's just that their peak power is gonna slightly decrease after some time. And so this is not the limiting factor. I would probably see the limiting factor being the other components, such as the inverters. The question is, how long can they live? If they can sustain for 25 years, that's great. However, the warranty sure isn't that long, and who knows? So Will they last at least the 12 years? That's the question to be answered. Getting to an end here. It was quite fun, wasn't it? At least some of the part. Now, probably the most demanding part was acquiring the data, gathering the data of the roof plane slopes and the measurements in case they're not provided in the documentation. However, the rest can be done just with a computer in the warmth of your office. Now, if I were to do it again, I would probably just start by analyzing the kilowatt hour per kilowatt peak potential. For that, you don't need to actually have the pan layouts drawn. I'm not sure whether I said that in this order. However, it's the order in which you'd probably be tackling the issue. Now, one thing to note is that in case you are planning a grid-connected system, the grid provider is most likely going to want you to install a 4-quadrant electric meter, as well as perhaps some other measures, so just keep that in mind. Now, although I haven't had an experience with physically building a system as big as this, I once built a smaller system just with one inverter and a couple of panels on a camper van. And although this system is much more robust in the actual size, the rest is kind of similar, but for the electrical part, which requires some knowledge and some skill. So is it possible to do it yourself? Definitely, but you will need to have some gear for that and the will to do so. Now, in case you followed me up until this point, I am sure that you were successfully able to design a PV generator for yourself, for your building, for your project. Now, if there's anything that you'd like me to cover more deeply, let me know. Perhaps be it analyzing the wind potential as other renewable source, or anything that you think I haven't covered enough. Let me know, let me know, let me know. Now may the sun shine on you with great intensity as always, and hereby I declare this part of our project finished. Take care.